Hello, good morning, friends. And today, last time I taught you the basics of the vectors, and today I would be teaching inner product space, which is related to the concept of the space, and it is also involving the concept of the vectors in the inner product space as well. So, if you see the overview of the topic it is orthogonal basis and inner product space, and one of the very famous mathematician theorem that is called Graham-Schmidt orthogonalization process. So all these things are the part of the functional analysis, which is called the abstract mathematics and which is called pure mathematics. So but here the pure mathematics is having a very little applications in applied mathematics. But let me tell you, pure mathematics is equally applied in engineering sciences, and that's what we are studying here. So whether you talk about any of the engineering sciences, everywhere physics comes, and everywhere we deals with the vectors, and everywhere the vectors need to be orthonormal or orthogonal, and it need to be normalized in some other way to have a finite dimension of that vector. So we will all see what is the real notion of the functional analysis in this overview of the lectures. And let's start with the inner product space, and that is called, what is inner product space? Let me define first that. Suppose if this is a plane of a vector, and which is represented by v, and there is a point which is called u, and there is a point which is called v. So I say that this uv belongs to this capital V, which is, and this uv is a vector which belongs to the vector space v. So anyways, this uv will be called inner product. This uv will be called inner product only when it is represented by this equation, that is u comma v, right? And this is nothing but this is exactly equal to u dot v. So this is like a dot product. Or if I suppose that u equal to a1 plus a2 and v equal to a3 plus a4, so obviously the inner product of uv gives us a1 a3 plus a2 a4. This is what. And looking at this simple definition, and looking at this simple meaning of the vectors, we can derive many of the properties of the inner product, and that properties might be for the property number one, that is symmetry. Symmetry in the sense that if inner product of uv calculated will be exactly same if it is calculated in this way by just changing the order of u and v and v and u, right? And second is that additivity, that is doing an addition. So okay, so if this is u plus v comma w, and for all this u, v and w belongs to v, then obviously this will be equal to u comma w plus v comma w. Anyways, so this is called additive property of the inner product space. And the third property, which is called homogeneity. In this homogeneity property, we are multiplying any scalar. For example, we have again uv vectors which belong to the product vector space v, and if you multiply any scalar k u into v, then it does not make any sense. The scalar comes as a common factor out, and it is getting multiplied with the inner product result of the two vectors u and v. This is the third property of the inner product space. And this is the fourth property, which is called positivity property. In this positivity property, if we have the same inner product vector, that is v comma v, okay, the fourth property says that if we have the same vector v comma v, this is exactly greater than or equal to 0 if v is equal to v, which belongs to the capital V, which is a vector space. And if this v and v equal to 0, then ultimately one of the vectors is 0. That is why it is 0. So this is called positivity property. So depending on this property, the whole chapter has been expanded, and this whole chapter has been given a solid base upon this one. So there is a two terms which is called Euclidean space. So let us understand what is this Euclidean space. So in the Greek times, the Greek mathematician used this term which is called Euclidean space. Basically, Euclidean space is a vector space of a real numbers. So everywhere you can see real numbers, everywhere you can see real numbers. When we deal with the real numbers, so that vector space is called Euclidean space. Probably we also deal Euclidean space with the complex number, which is represented by this way: z1, z2 and z3 and z4. So it means that this Euclidean space is also represented for real numbers and is also represented for complex number, right? So if I say that this real number Euclidean space is also related to inner product space if it consists real number vectors and if it contains complex number vectors, then this whole terms becomes a real inner product Euclidean space, inner product E space, and similarly this becomes complex inner product Euclidean space. So this was just the simple outline of the whole basic theory regarding inner product space. But as I said you that we have to deal with the orthogonal basis, and we have to also deal with the orthonormalization, and we have to also deal with the famous theorem given by this two different mathematicians in the 90s and in the 18th century. In fact, if I remember the exact date, it was given somewhere around in 1920s and in 1878, something like that. So these two different mathematicians gave their own theory about orthogonalization and orthonormalizations of the vectors. How can we orthogonize and orthonormalize different vectors which is in the space? So we will talk about that in the later part, and we will also in these lectures we will see how we can solve different examples related to that. And everywhere, if you see in the GTU exam, most at least 1 or 2-3 questions generally comes from that this gram scheme process. So one question is every exam is sure from this process, so one needs to understand this process quite well. So anyways, so what is orthogonal vectors? So this is my basic concepts again to you. So probably in matrix chapter, if you have studied in your colleges, so probably if A is any square matrix, then A product of A into A transpose, or product of A transpose into A, if it is equal to unitary matrix, then this is called orthogonal matrices, right? Similarly, we can draw that concept, or we can draw that notion here as well. So I mean to say, if u, a small u and a small v which belongs to the vector space V, and if this u and v are orthogonal only and only if there is an angle pi by 2 between them. So any vector, for example, we can draw this way as well. This is a v vector and this is u vector. If it is having an angle pi by 2, then I can say that u and v are orthogonal to each other. So this is the condition that the angle between each other should be pi by 2. And similarly, if this in norm of u and norm of v, so why I'm using this double line? This double line is called norm, which is called norm, and this norm represents the length of the vectors. This norm represents length of the vectors. So for example, if this u is equal to a1 x plus a2 x, so obviously if I writing this norm u, then this will be equal to under root of a1 square plus a2 square, and this is what is called the length. And this modulus of u, it gives the absolute positive value of a vector, but this double line arrow, a straight line of the vectors, gives us the length which is called standard terms, that is called norm. So this norm, and if I write in this way, this u minus v, then this is called distance between the two vectors. If you draw these two vectors in space, this is u and this is v. So the distance between these two vectors is represented by this double norm, that is u minus v, which is exactly equal to v minus u. So this represents the distance and this represents the norm. So I mean to say that if the norm of the single vectors equal to 1 and the norm of single vectors v equal to 1, then these two vectors which are just orthogonal in the concept when theta is equal to pi by 2, then the condition, if this condition satisfies, then those vectors itself becomes the orthonormal vectors. Then those vectors becomes orthonormal vectors. So I hope you must have understood the difference between what is orthogonal vectors and what is orthonormal vectors. So basically, when vectors is having an angle of pi by 2 between each other, then that is called orthogonal vectors, and when the length of the individual vector is equal to unity or equal to the value 1, then that is called orthonormal vectors. Okay, so probably depending on this basic concept, we can also solve numericals, which is generally coming in every semester of the GTU exam. And how can we solve those examples? So let us see a few examples and then we can move on for further theory. Anyways, this is a vector, and out of this it is asking us which of the following matrices are orthogonal, and which of these following matrices are orthogonal with these vectors. Which of the following matrices are orthogonal? And the matrix first given is -3 0 and 0 2, and again matrix is given as
as strong as an ox.
2 1, and this is 5 and 2, right? So probably I have to we have just seen the concept of the orthogonal vectors in terms of the vectors, but when those vectors are the scalar quantity and represent. So anyways, so we have been asking this question, that which of this we have been given a primary matrices that is represented by this matrices, and we have another two matrices A and B, and we have to check this matrices whether it is orthogonal to that given vectors or not. So I'm supposing that the given vector is equal to u, that is -3 0 and 0 and 2, and this is the primary matrix is equal to V, that is 2 1 -1, and this is 3. So if I take an inner product of these two vectors u comma V, so ultimately it is not like a matrix multiplication what you have studied in the matrix chapter. It is totally different. Once we write inner product, it is totally represented by the dot product. So this first element will be multiplied with the first element of the second matrices, and the second element of the first matrix will be multiplied to the second element of the second matrix. So respective elements are multiplied. It is not like row wise and column wise what you have studied in matrices chapter. It is totally different. So it is here -3 into 2 and plus 0 into 1 and plus 0 into -1 plus 2 into 3. So ultimately this is -6 and this is 0 and this is 0 and this is 6. So -6 plus 6 and this is equal to 0. So in terms of a matrix, when the inner product of the two matrices is the value equal to 0, then that matrix, the given matrix, is orthogonal. Otherwise it is not orthogonal. So probably here the condition is satisfied, and we can say that this given matrix is orthogonal. This given matrix is orthogonal, right? Similarly, you can check this matrix with this matrix as well. So if you multiply again, if you consider this as a u, now if you consider this as a u, and now if you consider this as a v, so you multiply this again, so this becomes u inner product v, so that is equal to 2 into 2 4 plus 1 minus 5, and this is 6. So ultimately, if you just simplify, it is not equal to 0. So ultimately I can say this factors, or this matrices is not orthogonal with the given matrices. So this is where the concept of orthogonal we are deriving from the normal vectors to the matrices as well, specifically when it is a square matrix having basically same number of rows and same number of columns. Okay, so this was and another thing is that how we deal with the orthogonalization of the vectors when it is a given polynomial and when the given polynomial is having any conditions. So that's the next topic, that is orthogonal vectors in P3. This P3 means that polynomial, we have a polynomial, which means that it could be anything. It could be a1x plus, and it could be a2x plus a3x square plus a4x cube. So ultimately the highest degree we have, that is 3, and this is called a polynomial of a degree 3. So how to check whether those given polynomials is orthogonal among each other or not? And that's another type of questions which might be asked in your exam, or which you might encounter anywhere in the competitive exams related to this chapter as well. So let us see. What we basically do in this part is that we try to make a pair of the given vectors, and then through each pair we apply the given conditions, and then we solve it. So the question is that let us consider the vector space P3 having an order, and this is -1 and 1 is that the limit that we apply, that is -1 to 1. This is the lower limit and this is the upper limit. Okay, where it is given that the function p is equal to p of